All right, guys, so we finished off talking about the membranes. Now we're going to talk about how the cell gets its energy. And after that, we're going to talk about how the next unit after that is going to be more about the cell. But first, let's talk about how a cell gets its energy, how energy is processed. So things we're going to go through is going to be photosynthesis, how photosynthesis gets its resources, cellular respiration, how cellular respiration gets its resources, and then bioenergetics, how they work together. So photosynthesis is going to be taking light, photo, and creating energy, synthesis. So the energy are creating actually the chemicals that will create energy. So the energy of life begins as photons created by nuclear fusion traveling out of the sun at the speed of light. So that's happening at the center of the stars as the pressure is so great, those early elements are the nuclei are fusing together and making larger and larger things, and then we get those photons also created in that, and those get emitted throughout, and that's the packets of electromagnetic radiation that's being sent to us through space. All right, so electromagnetic radiation is composed of an oscillating wave of magnetic and electric fields which travel through space. The distance between the crests of the waves determines the wavelength, and the number of crests per unit of time determines the frequency. So if you've taken any physics, you probably have already learned about this a little bit. But so wavelength, the wavelength is going to be the velocity by the frequency. So as you look, you can see each wavelength or each crest there, and so a wavelength would be the amount of time it goes through that. All right, so the wavelength and frequency of the electromagnetic radiation in a photon determines the energy. A short wavelength means that it's hitting you more often. That's going to be high frequency, high energy. Long wavelength means it's hitting you less often. So it's low frequency, low energy. So when you see, if we talk about this in the terms of light with infrared light, infrared is going to be anything that has a longer wavelength than, a longer wavelength than red light. And if visible light is red, orange, yellow, green, blue, indigo, violet, Roy G. Biv, that's the visible light. So anything longer than that is going to be infrared. It's going to actually be slower. And it's actually moving so slow that our eyes cannot detect them. So we need to have something that picks up that infrared radiation. Now we know it exists, but we cannot, our eyes themselves cannot perceive that. Ultraviolet is going to be anything that has a frequency, a very high frequency, anything higher than our eyes can perceive. So that UV light is going to be anything that has a shorter wavelength than violet, and so a very fast frequency. So it got a lot of energy. And we know UV light exists too, specifically because UV can burn our skin. So we knew it existed even though we can't physically see it with our eyes. So again, sorry guys, visible light is going to be that Roy G. Biv. Roy G. Biv, you have your longer wavelengths at the red line and shorter going to the violet. So the wavelengths in between there are going to be between 400 nanometers and 700 nanometers. Anything above 700 is going to be too slow for us to see, so too long of a wavelength for us to see. And again, anything below 400 or shorter than 400 is going to be too fast for our eyes to see. So our visible light is just in this group. If you look at the electromagnetic radiation, so this, just to point out, this chart is actually opposite of the one before it. So red's on this side instead of over here. And you can see the wavelength is much longer. And as we go through our visible light, they get closer and closer and closer and closer and closer and closer together. So our visible light is just going to be in this section right here. Radio waves, microwave rays, and infrared waves are going to be things that our eye cannot detect, but those wavelengths are there. So radio waves have a very low frequency, a very high wavelength. Ultraviolet, X-ray, and gamma rays carry a ton of energy, and their wavelength is very short. The frequency is very high. So if you get exposed to a lot of UV, X-ray, or gamma rays, you are getting a ton of energy being focused in on your skin. It tends to be when you're overexposed to these things, you might get cancer. It can be a carcinogen. So, electromagnetic radiation is going to be the color, well, color is what we see is what is being reflected. So when we see a color like green, it is going to be what the object doesn't need, what it is reflecting, and it's absorbing the rest. So plants are green because they don't need green light. We see green because they are absorbing all the colors but green. So if you put a plant under a green light and no other light, that plant would die. It's not getting any of the light it actually needs. It's only getting the light it doesn't need. So in this case, green is being reflected and everything else is being absorbed. White light is going to be all light reflected, and black is going to be all light absorbed, which is why in summer, if you're wearing black, you tend to get hotter because that shirt is literally absorbing all of the color and not reflecting any of it back out. So pigments are going to be things that are absorb that light. These are how we get our colors. So pigments are going to be the thing that actually does the absorbing or reflecting of the electromagnetic radiation. So in the case of this blue pigment here, you can see that it is going to absorb the green and the red, but it is going to reflect the blue. So that helps us perceive our colors. So a person's shirt looks red because the red wavelength is being A, reflected or absorbed, or B, reflected. Did you say B, reflected? Good. All right, chlorophyll is a pigment found in plants. What color of light does chlorophyll absorb? White, orange, green, or all of the above? Did you say orange? Good. Can't be white because white is all the colors. When you see white light, it has everything. That's why when you shine white light through a prism, you see a rainbow because it has separated all those lights and you can actually see each wavelength for their own rather than all at once like we do when you see white light like coming through the room right now. The absorption spectrum is going to show us the wavelength, and we can use this when it comes to plants. You can use a spectrophotometer that's going to help you see where those wavelengths are. So this graph represents the absorption spectrum of chlorophyll. The two lines represent the two types of chlorophyll. There are two types of chlorophyll, chlorophyll A and chlorophyll B. So if you look at this, chlorophyll B is going to absorb here in this blue range, and then maybe a little bit in the red range. Chlorophyll A is absorbing more in the violet range, and then quite a bit here in the red range, leaving nothing absorbing well at all in the green range. And again, that is why we see plants as green, because they are reflecting that green. They're not absorbing it. Now let's take that a step further though. It's fall right now. The leaves no longer look green, or they're starting to turn at least. That is because now chlorophyll A and chlorophyll B are no longer doing their jobs, and the carotenoids are taking over, and they are actually going to reflect the orange and yellow, changing the color of the leaves via our eyes. So pigments, when the electromagnetic radiation is absorbed, the energy contained in the photon is transferred to an electron, and that makes the electron excited. That means the electron will actually go from a low energy state to a high energy state, so a higher energy level. So a photon, this packet of energy, comes in, and this electron that's just hanging out in this nice, we'll call this energy level 1, gets all excited, whee, and it jumps up to energy level 2. Now, just like if you have a caffeine buzz, you cannot stay in that excited state. You will crash. Same thing going on with the pigment. It'll get excited. It'll be it'll be in that excited state, and at some point in time, it will fall back to its regular state. The plants, the chlorophyll will actually capture that energy through a series of these energy transfer carriers. So an excited electron is very unstable at the higher energy levels. It must release its energy that it got from the photon. So in a pigment molecule, the energy can be released in a couple ways. It can be released in fluorescence, that glowing. It can be released at a reaction initiation, so actually causing that reaction to start to occur. And it can also happen in resonance transfer. So that's actually like a shaking transfer. If you may have remembered, and or if we didn't get to it because of the pandemic, if I discussed how sound travels, sound for humans, so it starts here in the vocal cords, and our vocal cords, we push air through from our respiratory tract, which shakes our vocal cords, and then the vocal cords shake the air particles, and they keep shaking, 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 shaking till they bounce off your eardrums, which shake that, which shake the inner ear bones, which shake the ear fluid, which then shake little tiny receptor hairs inside the inner ear, which turns it into electrical impulse. So all that shaking is resonance transfer. Plants are very adept to capturing these minor resonance transfers, these minor shakings with these little carrier molecules right here. Fluorescence is going to be light, so when something glows. So if an electron has no other way to release its energy, it will drop back down to its ground state. As the electron drops back down to its ground state, it was released in a photon. That photon is released in that packet of light, and it's not near as bright as it was when it was absorbed in the first place. Every energy transfer loses a little bit of organized energy. But so that would be fluorescence, releasing that little packet of light as fluorescence. So any glow in the dark things you see, they're releasing photons that it didn't have anywhere to go. That energy didn't have anywhere to go. So as it dropped back down to its state, it's releasing those photons of light, creating that glow. For reaction initiation, that excited electron may be enough energy to start the ball rolling for an energy for a chemical reaction. Like iodine, it's kept in a dark container. If you put iodine liquid into a clear bottle, it'll actually start to react because light, those photons, will actually start to react it and break it down into its ions. And then there's resonance transfer. And so in this case, we have, and I talked about through sound, but here it is with light going through the pigment molecules of chlorophyll. The photon was absorbed. It shook until it got to the reaction center. So this is all energy transfer, resonance transfer, and then out through the electron. So the energy will continue to move between donor and acceptor pigment molecules without releasing the photon. So the photon isn't released. No light is being released. That shaking is being transferred all the way through. So as energy from photons is transferred to electrons, the electrons move to lower energy levels and are more stable, move to a lower energy level and are unstable, become excited and become more stable, become excited and become unstable. Sorry, get your answer. Did you say D? Good. They absorb the energy, they get all excited, and when you're excited, you are unstable. The process of electrons passing energy to electrons in neighboring pigment molecules is known as fluorescence, resonance, photon transfer, or activation energy. Get your answer. Did you say resonance? Good. All right, we will stop there. We talked a little bit about how energy is absorbed through pigments, how we perceive light in both visible and non-visible spectrums, how wavelength and frequency affect that. And we also talked about how that energy transfer can be released from its excited state of the absorption of the photon packet. All right, so we are starting to talk about photosynthesis right now, and we will move on more about photosynthesis in the next video. All right, everybody, have a great day.